Come on. There we go. Okay, so we are continuing to build up our toolkit for understanding the graphs of functions using derivatives. So today, I want to quickly review some of the stuff we spoke about last time about increasing and decreasing and convexity. Then we're finally going to connect this to the second derivative. So this will be the proof that a function is convex, which means it opens up if the second derivative is positive, and it's concave, so it opens down. The second derivative is negative. So we saw this for parabolas last time. We saw in the special case of a parabola that the upward opening parabola is convex and the downward opening parabola is concave. And now we're going to generalize that to any function with second derivative of known sign. And then we're going to do something else, which is among the most common applications of this in science, is getting approximations, using a tangent line approximation to simplify some equation. Okay, so that's the plan. Now, you see my error again in session 30, but good. First, let's remind ourselves of what we spoke about last time. So the punchline of our proof from last time was that the sign of the derivative tells you whether the function is increasing or decreasing, right? So we saw several cases. Strictly increasing means that whenever, well, you remember the definition of this, if a is less than b and f is strictly increasing, then this means that f of a is strictly greater than f of b, with no equality allowed. So we know that condition is true if the sign of the derivative is entirely positive on the interval. Similarly, it's decreasing, so if a is less than b, f of a is smaller than f of b. Yeah, sorry, do I have this backwards? If f is increasing, yeah, I have this backwards. What am I doing? So if f is strictly increasing and b is larger, then it gets bigger at b. So f of b is greater than f of a. Man, rough day. Okay, so we saw this, we proved last time using, I think, the mean value theorem, and then you have the similar fairly obvious generalizations. If the derivative can become negative, then you no longer get these strict inequalities, you get less than equals and so forth. And then we started to speak about convexity and concavity. So the idea was that something is convex, or convex, if you don't put a word after it, it means convex down. So convex down means that it points down. I think of the v in convex like a v. So a function which points down opens up. So convex down means concave up. And the idea is that that's true if always the line segments joining 2 points lie above the graph. So this upward opening parabola is indeed convex, because if I draw this line segment between 2 points on the graph, the line segment is everywhere above the graph. Great. Same thing, reversed, for concave or concave down, that if I pick 2 points on the graph and join them, then this thing is going to lie below the graph of f. So this is the geometrical intuition for convexity and concavity that we saw last time. Okay, has this reminded you of any questions or brought new questions to mind about this stuff?
I do not have any thoughts or questions.
Sweet. Okay, let's do a couple quick warm-up review things then. So here's a graph that does, a few interesting things, and at each of these points, a through j, we would want to determine the sign of both the first and second derivative if it exists, and if it doesn't exist, we'll say it's undefined. So first let's look at this point a. What is the sign of the first derivative here?
Negative.
Yeah, so f prime is negative because the function is decreasing. You can cheat and assume the results about concavity, that a function's second derivative is positive if it opens up, and the second derivative is negative if it opens down, even though we haven't proven that yet, but we will shortly. So what's the sign of the second derivative at a?
Positive.
Yeah, so second derivative positive. Okay, what about b for both?
First is 0. Second is going to be positive.
Yeah, so again, f prime, double prime is positive. How about c?
Is going to be positive, and I cannot entirely tell. I'm inclined to believe 0.
Yeah, I think it's hard to tell exactly, but I think the function's drawn so it's supposed to look like 0 here, because it's turning from opening up to opening down. So I think the author intended, or the artist, whatever, the plotter, intended for this to look like the second derivative is 0. Good. How about D?
First is positive, second is going to be negative.
Good, so it's opening down. How about E?
First is 0, second is negative.
Good. Now we get a kink. What happens at this kink at point F?
It's going to be undefined, and the second derivative is going to be undefined as a result.
Yeah, good. If the function itself is not defined at a point, then it's... Wait, is that true? Is it always true that if a function is not defined at a point, then its derivative is not defined? Huh. Well, in any case, it's
Well,
certainly true here.
isn't the definition of second derivative the derivative of the derivative?
Yes, but... yeah, that makes sense. So, good. So we could in fact prove this if we wanted, that whenever the first derivative is undefined, then the second derivative must be undefined, because if the function does not exist here, then it certainly can't be continuous there. And if it's not continuous, it can't be differentiable. Good, good. I just confused myself for a moment about why that was true, but you're right. Yeah, certainly both must be undefined. Okay, how about G?
It's going to be 0, and the second derivative is going to be, let's see, 0.
Yeah, it has to be 0 as well, because this is just flat at this point. Good. So I think similarly we see it should be undefined here because there's a kink. Here it looks like to me that the tangent line is horizontal and it's also inflecting, so it's changing from opening up to opening down. So I think they're both 0 here would be my guess. And then this one looks like the function's decreasing and it's moved to opening down, right? So f double prime is also negative. Good. Not so I mean, it's a bit repetitive, but good to get that intuition solid. Okay, so here's a fun, I guess, challenge to figure out all of the important features on a graph, like maxima, minima, inflection points, where the concavity changes and things like that, and try to get an accurate graph without using a graphing program, just by looking at this and taking derivatives. So first, well, what obvious features, if we were plotting this function, what are the first things that you notice where this function is going to do something interesting?
Undefined when x equals 1.
Yeah, or minus 1 in fact, right? So at 1 and
right.
minus 1. Yeah, we have two asymptotes here. So in fact, this function is an example of an even function, as we were talking about today, right? Because it only contains even powers of x. Here's 0, this is x to the 0th power. So in fact, if we want to graph it, we know it's completely symmetric about the y-axis, so we can basically just find all of the interesting points on one side, say for x positive. We'll find all the interesting stuff here, and then we don't have to repeat the analysis over here, because we know it's just a mirror image. Good. Okay, so we know it blows up at these two places. Let's try to figure out where it's increasing or decreasing. So what should I do to compute the first derivative of this guy?
But before we do that, I am curious. Can you split the numerator? I feel like I've made this mistake before.
So yeah, if you have a plus b divided by c, you can break that into two fractions.
I meant to say denominator.
You cannot split the denominator, right? That's not how division works, right? If you
Right.
you can check that pretty quickly. Say for instance, 1 over 1 plus 1, that's a half. And then you would say, is that the same as 1 over 1 plus 1 over 1? Well, that's 2, so it couldn't possibly have worked. 1/2 in most countries is not the same as 2. Okay.
Just checking.
Good. Good to have the algebra on lock, though. So, okay, so I think we have to quotient rule this bitch. So what should we write here?
So we're going to have 2x times x squared minus 1 minus x squared times 2x
Good.
all over x squared minus 1 quads t squared.
Good. Okay, I will simplify this for you because we see something nice happens. This, when we distribute this on the first term, there's a 2x cubed, but then you subtract off a 2x cubed. So those two things cancel, and you're left with just upstairs minus 2x, and downstairs x squared minus 1 quantity squared. Okay, so we see, of course the derivative also blows up at 1 and minus 1 because the function blows up there, but we see that the first derivative is going to be, let's see, it's 0 at 0, right? So we know when we plug in f of 0, which is 0, the first derivative vanishes. So there's a horizontal tangent line here. And then when we go a little bit to the left or to the right, I think this thing, say if we plug in, some small number, we're going to get something negative, right? Because if we plug in like a tenth, we're going to have something positive upstairs and then something like 1/100th minus 1 downstairs, right? So that's going to be negative. So I think this thing has to have a local maximum at 0, which is what we would expect because the derivative is 0 there. So it's doing something like this, which I think makes sense, right? Is everything good here? Yeah, then f is decreasing here, which is good because we plug in a small positive number, we get something negative, so it seems like it's decreasing. Just for fun, let's take the second derivative to figure out concavity, to see what's going on outside here, outside these asymptotes. So what's the second derivative of this guy?
So this is going to be thinking -2 times x squared minus 1 quantity squared minus -2x times, let's see, I guess we're going to need to chain rule here.
Yeah.
So I guess begin left parenthesis, and you're going to have 2 times x squared minus 1 times 2x.
Yeah. That looks right. And then all over now this guy to the fourth, right? So
Right.
this one to the fourth. Okay, so there's a lot going on here. I'm gonna kill these two minuses. So this is a plus 4x squared. Maybe we don't really need to simplify this because it seems like it's going to be a bit of a mess, but we can at least figure out the sign of this guy at a couple interesting points, right? So we think since the function opens down that this should be negative if I plug in 0, and indeed if I plug in 0, the second term goes away. The first term is going to be -2 over something positive, so indeed it's negative here, so the concavity indeed is downward. So it looks like it blows down here. Fuck. Like this. On the other side, let's see, it looks like coming from the right, if I plug in something a little bit bigger than 1 slightly, this thing is positive and getting large, so it looks like it comes back down on this side, so it should, I think, open upwards out here. And then what happens finally when I go to plus or minus infinity? So if x gets very large, what does this function approach? Or in other words, what is the limit as x goes to infinity of this guy? We can't prove this yet, but you can kind of guess.
I believe it approaches 0.
No, so this guy goes to 1, right? Good, so the way to see that, which we'll prove later, right now I'm just going to hand wave a little bit, so this is not going to be very intellectually satisfying, but we'll prove this later in this chapter. The way to think about this is look at this and think x is now huge. X is like 10 bajillion or something. If x is huge, then x squared is even bigger, and 1 is effectively nothing, right? So x is so large that, compared to x squared, 1 is negligible. So we just drop that term, and then we say that's approximately, when x gets large, approximately x squared over x squared, which is 1, right? So you can kind of cheat a little bit. If you want to find the limit of a ratio as the variable gets large, you just cheat and drop every term that is subleading, right? By subleading, I mean has a smaller power of the variable. And that's, kind of the hacky way to do it. We'll prove this later with something called L'Hopital's rule. But anyway, so that's what the function does. Blows up, concave down, concave up, goes to 1 at the either side. Good. Thoughts on this?
So is the idea behind your hand wavy that it is so large that addition and subtraction doesn't affect it?
Or it does, but it only affects it by a very small amount. If we're trying to say approximately, we're trying to approximate this thing when x is large. You say, x is so large that, as you say, approximately subtracting 1 doesn't change it, right? It only changes it by a very small amount, which we'll ignore. Yeah, good. Similarly, if you wanted to ask what happens to like x squared, or let's make it a little more interesting, 3x squared plus x over 2x squared minus 9x plus 5, if you wanted to ask, what does this guy tend to as x tends to infinity? What is the limit of this thing as x goes to infinity? And again, I'm hand-waving, but you can look at this and say, well, if x is a billion, then a billion squared is so much larger than a billion that we can just drop this x. Same thing with this. Same thing with the 5. So it's approximately 3 halves. And indeed, the limit is x goes to infinity if this ratio is 3 halves. So you just consider the leading piece. And I mean, again, I hasten to add that we will actually prove that. I'm not just bullshitting.
Okay.
Good. Okay, other thoughts on the graphing?
I have no further thoughts.
Sweet. Let's double check what we said. So here I plotted with Mathematica to do some answer analysis. As you can see, it's basically exactly what we expected. Qualitatively, it goes to 1 at either side. It blows up at x equals plus or minus 1. Concave down here, which agrees with our check that the second derivative is negative there. The first derivative vanishes at 0, so there's a local max. You can probably tell now that, I mean, if you're looking for local maxes and mins, the first derivative is only enough to tell you that something is going to be a local max or min, but not which one it is, right? A max or a min. So you've probably figured out that the second derivative is interesting because it tells you whether it's a max or a min, right? So if you find places where the first derivative vanishes and want to know whether it's a high point or a low point, you just ask, is second derivative positive or negative there? So that's one reason why it's nice to have the second derivative, because we know this was a max here. Okay, good. Enough review and plotting. So let's finally wrap up that convexity and concavity stuff. So I remind you, last time we had a first definition about, as we saw a moment ago, about these, connecting 2 points and then asking whether it's above or below the graph. And then last time we kind of showed that that definition was equivalent to this algebraic one, right? That if you have any 3 points, a less than x less than b, this interesting looking inequality holds, where f of x minus f of a over x minus a is less than f of b minus f of a over b minus a. This has to hold for every x between those 2 endpoints. So notice the right side is a constant. This is just a number. On the left side depends on x. So that has to be true for every x in the integral if it's convex. Concave, similar, replace with a greater than. So our goal for today is going to be to prove, in fact, we'll prove both directions, that convexity is related to positive second derivative, which we'll prove in the following sense, that if it's convex at a point and differentiable, then we're going to prove that f prime is increasing. And if f prime is increasing, then by what we saw last time, that means if f double prime is defined, then it's positive. We'll also prove the other direction. So if there's a second derivative which exists and it's everywhere positive on an interval, then the function's convex. So we have to prove one direction and the other direction. I don't think I do it for, you can just reverse all of the signs if you want to prove it for concave. The proofs are very similar. Okay, so that's the plan. Thoughts on the roadmap or the goal?
It kind of looks like this is assuming that f of x is less than f of b.
Ah, I see. So you say,
Yeah.
yeah, it's the only difference is that it's x also appears in the denominator, right? So, yeah, you could, if this were b minus a on both sides, then you would just genocide all of these other terms, and it would be saying f of x is less than f of b. But there's a small difference because you also need to compare, this numerator to x minus a in the bottom. So that's the only thing that makes it non-trivial, right? That there's x's in 2 places. Good observation. Other thoughts?
Dividing is weird.
Why is dividing weird?
I don't know, because it seems like x is going to be, well, we see that x is less than b, and therefore we're dividing by a smaller number on the left side, theoretically.
Yeah, good. Yeah, so we're basically, as you say, we're comparing, we're both dividing a smaller number, but also in principle, uh, this is related to how quickly f is increasing on this interval, right? Because you're comparing the difference. I mean, it's kind of like it's literally a slope, right? This is kind of a change in y over change in x related to your input point x. And this thing is, again, another slope. It's a change in y over change in x, but between the endpoints b and a, right? So it's it's weird because, as you say, both the numerator and denominator are changing as you slide x, but what you can think of it as is really just comparing two slopes, if you prefer. Good. Okay, let's try to prove some shit then. Okay, so the proofs are a bit hard, so we'll need a lemma, actually two, a lemma going in either direction. So here's the first lemma. So we're going to assume f is convex. So again, that means convex down or concave up, so it opens up. And we claim that if f is differentiable at a point A, then the graph of f lies above the tangent line through a f of a. So I've drawn a few tangent lines here. You'll see that, I mean, this isn't quite the same as the definition of convex, which is saying that if I connect 2 points, then that line lies above the graph. But you can kind of see that that statement is very similar to the statement that the graph is going to be above the tangent lines, right? You can just kind of see that if I draw all these tangent lines, because the graph is kind of bending upwards, it, in some sense, is running away from the tangent line, right? Because it bends upwards at each point. The graph is like trying to curve away from the tangent line, so to speak. So we're going to prove that, indeed, the graph always lies above the tangent line. And then we're going to prove one related thing in the same proof. Furthermore, since f is differentiable at a, we're going to prove that f prime of a is smaller than the secant line slope between a and a nearby point h, if h is positive, and f prime of a is greater than that secant line slope if you're comparing to a point where h is negative. So why is that? Let's just look at a couple points to convince ourselves that that makes sense, sort of an exploration sort of thing. If this is a and here's a plus h, where now h is positive, and we get this secant line slope, what is the theorem saying? It's saying, well, the derivative at a, which is that's the tangent line slope, that slope is less steep than the secant line slope. And indeed, we see that's true, right? Because here the tangent line at a is less steep, and this secant line slope is more steep. And then we have a similar statement that if h is negative, so now you're comparing, I don't know, I'll just write a minus h, I guess. Now you're comparing the secant line slope to a point to the left of a. Now you see that the tangent line slope is larger, because here it's positive. Here the secant line slope, the way I've drawn it, is negative. So indeed, the tangent line slope is greater if I'm comparing it to a point to the left. So it's slightly slight or generalization, not generalization. You can see it's related to the definition of convexity because it has to do with connecting these points and comparing them to some behavior of the graph. But the lemma, the only thing that's different about the lemma is now, rather than comparing these lines connecting points on the graph to the graph itself, now we're comparing them to tangent lines, which is going to help us build towards derivatives. Okay, questions on the statement of the lemma?
I do not have any questions.
Cool. Let's prove this bitch. Good. Okay, so this is a bit dense, but we have two directions to go. Well, yeah, we have to prove it for both the positive h and the negative h. So here's the positive h part, and I'm going to pick 3 points, in fact. So 0 is less than h1 is less than h2. So remember this definition of convex we had a while back says that if it's convex, this thing holds whenever you have these 3 points, a less than x less than b. So if I'm going to use that definition, I'd better tell you what these 3 points are, a, x, and b. So I apply that definition where a less than x less than b are a, the point where f is differentiable, which was in the statement of the lemma, x will be a plus the first number, and then b will be a plus the second number. So now we know this right side is bigger than the middle because we've assumed h2 is bigger than h1. Okay, good. So we picked those 3 points. Now I'm just going to go back to convince you I'm using the definition correctly. I'm supposed to compare these two slopes and put in my x on the left side, but put b in its place on the right side. So I do that. This is that same inequality, but now x, we said, is a plus h1, and in the denominator this is supposed to be x minus a, but if x is a plus h1, then of course a plus h1 minus a is just h1. So I'm just convincing you I'm plugging into the definition correctly. That's the left side. The right side is supposed to be b, but this is b, so I put in b as the argument to f. The same thing downstairs, it's b minus a, but if this is b, then a plus h2 minus a is h2. So just emphasizing that this is definition of convexity, just with a clever, a clever choice of the points. Okay, so what we're saying is that this thing, but now we can take a limit is what I'm claiming, because this is telling you that the secant line slope between a and a point a plus h1 to the right, this thing is going to be smaller than the same secant line slope through the same point a, but a further to the right point a plus h2. So the idea is now to take the limit as h1 goes to 0, because taking that limit on the left side is going to give us the derivative, right? So this inequality we got from the definition of convexity is just telling you that, you know, this thing, this difference quotient, whose limit defines the derivative, is always upper bounded by the secant line slope. Or in other words, the secant line slopes decrease as h gets smaller. So that's the statement which we need to prove the first part, right? Which we were trying to prove that the derivative is less than the secant line slope if h is positive. So that's the first thing we needed to prove. This is related to the other thing that we needed to prove, because if this slope is smaller than the secant line slope, then that means the secant line lies above the tangent line. Why is that? Because if the tangent line slope is smaller than the secant line slope, I should go back to that other drawing. Damn it. Yeah, so if the tangent line slope is less than the secant line slope, the way that it is here, for instance, here the secant line slope is more steep, then this is the statement that the graph lies above the tangent line, because the secant line, by definition, connects 2 points on the graph. So if this is steeper, then the point on the right must be above the less steep line. Okay, so that proves the thing we need when h is positive. Now, I've shortened it, but you can see that the argument with h negative is going to be very similar. If h is negative, now we just pick 3 points, h2 less than h1 less than 0. So again, I have to pick my 3 points to apply the definition of convexity, but now I pick them with h negative. And if that's true, then you now need the direction of this inequality to flip, because, well, you can think of this, if you prefer, as dividing by a negative number and reversing the sign of the inequality up here, or you could just think of it as when I plug into the definition of convex, now the identity of a, x, and b are different, right? Because now I've rearranged them so that we have h negative and h2 less than h1 less than 0. So either way to see it, you see that the direction of this inequality now needs to flip relative to this one. So similar argument, you get that now this secant line slope is greater than this secant line slope, and again we can take the limit now as the h1 approaches 0 from below, which defines the derivative at a, and now we see that that derivative is upper bounded by the secant line slopes between a and nearby points to the left. So here h is negative. Okay, so again, we get two different inequalities where the direction reverses depending on whether h is positive or negative, but in both cases, the first sentence that the graph lies above the tangent line is true in both cases. So if the secant line slope is here going to be smaller than the tangent line slope, then that means that the point connected to A by that secant line again lies above the tangent line. It's true in either direction. Okay, this one's a bit dense, but thoughts or questions on lemma 1?
I do not have any thoughts or questions.
Okay. Good. Okay, with the lemma now proving, well, sorry, I'll give you one more picture to convince you of this, that because I think that last sentence I said it didn't sound very convincing to me when it came out of my mouth when I was saying that in both cases it should be true that the graph of f lies above the tangent line. It didn't sound very convincing to me, so I'm glad I put in more pictures. The things that we proved are that, let's see, these slopes in this case are increasing as we take h1 closer to A, right? Here it's negative, but here it's less negative, so it's increasing. And the other direction, if h is positive, so now the slopes are decreasing as we take h closer to A, right? Because this slope is less steep than this slope. But the sentence which didn't sound very convincing a moment ago was that even though the direction of the change in slope is different on these two cases, both of them imply that the graph lies above the tangent line, because the tangent line here looks, that's bad thing to draw. Here we go. The tangent line at A in both cases, even though the slopes are going in different directions, increasing or decreasing as I go to the left or right, in both cases the blue point on the graph lies above the tangent line. That's what I was getting at. Okay, good. Now we have a very, very short proof of the first thing we wanted to show. So this is the first direction, that if the graph is convex, which means it opens up, then the derivative is increasing, which means the second derivative will be positive, or I guess technically greater than or equal to 0, because I didn't say strictly increasing, but I think it's actually true that it should be strictly increasing. Okay, why is that true? So let f be convex, so again it opens up. We pick 2 points, a less than b, and suppose f is differentiable at both of those points, at a and at b. And then the claim is that the derivative at a is less than the derivative at b. So again, this is the statement that f is, I really should say strictly, f prime is strictly increasing. Okay, how do we prove that? Well, we use those 2 parts of the lemma that we just proved. Remember, we have this lemma that tells you that the derivative is less than the secant line slope if h is positive. The derivative is bigger than the secant line slope if h is negative. So we'll just copy that over almost directly, but now we're going to apply that result with a very clever choice of h, right? So here we've chosen h equals b minus a. Clearly b minus a is positive because we've assumed a is smaller than b. So we're free to apply that part of lemma 1 with h equals b minus a. That's a very clever choice because that means inside f we have a plus b minus a, which is simply f of b. So with that clever choice of h, we get f prime of a is less than f of b minus f of a over b minus a. And now we can play the same game and just reverse the directions with the negative h version. So we proved that the derivative is bigger than the secant line slope if you compare when h is negative. How do we get a clever choice of negative h? Well, just reverse these two, because we assumed a is smaller, so a minus b is now negative. So you plug in a minus b, but now apply this to the point b instead. So you apply this to the point b with h equals a minus b. So that's why b appears here and b appears here. So we're applying the lemma twice. One with a and a positive h, one with b and a negative h. When you do that, the same clever thing happens. B plus a minus b. Oh, yes, this is right. I skipped a step here, but as you see, this, I thought I typoed for a moment, but then I realized that I was just being clever. You can see that this is, of course, f of a minus f of b over a minus b, but the skipped step is multiplying top and bottom by minus 1. So of course we can do that. If you multiply by minus 1 on the top, you get f of b minus f of a, and minus 1 on the bottom gives you b minus a. Good. So now that clever choice allows us to conclude that f prime of a is less than f prime of b, because f prime of a is less than this number, but f prime of b is greater than that same number. So we have a chain of inequalities. F prime of a is less than the secant line slope, which in turn is less than f prime of b. So we have this chain, and combining those inequalities in the chain gives us what we wanted. That derivative at a is smaller than derivative at b. Good. Okay. So tricky choice of h, but I think it's very elegant. It's clever once you see it. Enlightening, perhaps. Okay. Good. Thoughts on this theorem?
You may have already mentioned it, but I see in the f prime of b that in the trying to remember denominator you have a minus b in the first.
This thing you're talking about, the a minus b and b minus a?
Yeah, I'm just figuring out what. Oh, okay, now I see.
Yeah, you see what I did? This is f of a minus f of b over a minus b, and then I multiplied by minus 1 on the top and bottom, right? To get to this.
Yeah.
Algebra. Multiplying by 1 in a clever form. Minus 1 over minus 1. Multiplying by 1 and adding 0 are the best tricks. Good. Other thoughts?
I have no further thoughts.
Cool. Okay. Now we want to go the other way. So we showed that if you're convex, then your derivative is increasing. Now we want to prove if your derivative's increasing, you've got to be convex. That's the other thing. So we'll need a lemma again, since both of these proofs are kind of hard, so I'm calling this lemma 2. So remember what we're trying to do. We're trying to show if your derivative is increasing, then you're convex. So in this lemma, we're going to say suppose you're differentiable and your derivative is increasing. So f prime as a function is increasing on the interval. Then the conclusion is that if you have 2 points, a less than b, but the function's value is the same at those 2 points, f of a equals f of b, then f of x is less than f of a, which is the same as f of b, everywhere in your interval. So in other words, this kind of makes sense, because if the derivative is increasing, then this is the statement that the function itself cannot be smaller than its value at either of the endpoints, f of a and f of b. These you can't have. Maybe I should draw a picture, make it clearer. So if you have something like, this is what we're proving can't happen, right? So maybe there's something like this. So there's a function where f of a equals f of b. So again, you end where you start. It's kind of like Raleigh's theorem. F of a equals f of b. The reason this can't happen, which is, we're claiming that you can't get anywhere bigger than your value at the endpoints. So the point where the claim would be false is, somewhere up here. The reason this can't happen is then the derivative would not be increasing anymore. And I'll convince you of that in the proof. So maybe I'll just go through the proof and then show you in the picture why this is breaking. So to show that f has to always be smaller than its value at the endpoints, we're going to suppose by way of contradiction that that's not true. That there's some point x where it's greater than the value f of a, which is the same as f of b. So somewhere it gets bigger. Now, we proved last time that there's a maximum which is achieved because f is differentiable, hence continuous, on this closed interval. So the maximum of f occurs at some point x0. So that's the blue point, which I've drawn here. So I'm trying to draw this to be the maximum on the interval. And since there is some value f of x which is greater than f of a, then this maximum point, x0, must necessarily have a function output which is also larger than f of a. Right? Because by definition the max is greater than or equal to its value everywhere else, but we've said that there's one point which is greater than f of a. So the x0 output has to also be larger than its value at the endpoint. Now we proved last time that those maxima can only occur at three types of points, right? Either you're at an endpoint, which here is ruled out, because we're assuming that this thing happens somewhere on the open interval, so it can't be that one. The other option is the derivative could be undefined, but that can't happen, because we've assumed f is differentiable on the interval. So the only option left for a maximum is that the derivative is 0. So there's some point x0 where the derivative vanishes. But now comes the clever trick. We're going to use the mean value theorem. What are we going to apply the mean value theorem to? Well, remember, the mean value theorem tells you that there has to be some point in this interval where the tangent line slope is the same as the secant line slope. What secant line slope do I mean? I specifically mean the secant line slope secant line slope connecting a with x0. Right, so this is the secant line slope. The mean value theorem guarantees that under these conditions, there has to be some point in this interval with a tangent line slope that has the same secant line slope. So the way I've drawn it, it looks like that happens about here, right? This point has the same tangent line slope, modulo bad drawing, as this secant line slope. So let's call that x sub 1. MVT guarantees that there has to be such an x sub 1. Now we get the contradiction, because at x sub 1, this slope, this tangent line slope, must be non-negative. It has to be greater than or equal to 0, because the tangent line slope is the same as the secant line slope, and the secant line slope must be positive, non-negative. Why? Because the numerator is non-negative, because we assumed f of x0 is greater than f of a. The denominator is certainly non-negative, because x0 is greater than a. So this secant line slope is a ratio of non-negative quantities, and is thus also non-negative. So we have found a point x1 where there's a non-negative tangent line slope. That's the contradiction, though. Why is that a contradiction? Because by construction, x0 has a tangent line slope where f prime equals 0, right? So I'm just going to highlight the two things that are a contradiction. The tangent line slope is 0 at this point. The tangent line slope is greater than or equal to 0 at this point. So here, f prime is greater than or equal to 0. That's a contradiction because we've been told f prime is increasing. So the tangent line slope must get bigger going from x1 to x0. Strictly bigger. Has to get bigger. That's not what happened in this picture. In this picture, the tangent line slope got smaller. It went from a positive slope to 0 slope. So that's the contradiction. That's the Bank of Scotland, because we assumed in the theorem statement that f prime is increasing. So good. It's fun. It's a bit tricky, but the point is that if your derivative is increasing, then you can't beat the value at the endpoint. You can't go above the endpoint value under these conditions. Good. Thoughts on this lemma?
I do not have any thoughts.
All right. Let's prove the converse then. So again, it's a common thing in math that when you have a good lemma, the proof of the theorem should be very crisp. You know, often the lemma is kind of a pain and it's very technical to go through, but once you have the lemma, the proof of the theorem should be very nice. So this one is, I think. This is the other direction. As I said, we wanted to show that if the derivative is increasing, then you're convex. Okay, let's prove it. So again, we pick 2 points a less than b on the interval. I should have said on an interval, but so f is differentiable on an interval, and a and b are points in the interval. We're going to do the same trick, which we've seen, I think, a couple times now. We saw this also in the proof of Raleigh's theorem. Remember when I said we're going to cook up this weird, or no, sorry, not in Raleigh's theorem. It was in the proof of the mean value theorem, right? Yeah, mean value theorem, using Raleigh's theorem. We cooked up a function which was obtained by taking our original function and then subtracting off a particular line, right? This is a constant, this slope, times x minus a. So this trick is very nice because, as we've seen several times, if you plug in, say, g of a, well, x minus a when x is a minus a, which is 0, so this term goes away. This tells us that g of a is the same as f of a. The other trick is if I plug in b, well, b minus a cancels the b minus a downstairs, and I'm left with f of b minus f of b minus minus is a plus f of a. So this is back to f of a. So we cooked up a function which satisfies the conditions of the lemma, right? Remember the lemma told you that you had to end where you start. So your function has to take the same value at the two endpoints. So g satisfies that condition, which is very nice. The other thing is that if f prime is increasing, we can just differentiate both sides of this equation. This goes away. This goes away as well, because the derivative of a constant times x is that constant. So if f prime is increasing, then you see g prime is also increasing, because g prime is just a constant offset from f prime, right? G prime is just f prime minus some number. This is just some number. So if one function is increasing and you just subtract a number, then it's still going to be increasing. The value has changed, but whether it increases or decreases hasn't changed. Okay, so that's good. It's good because now this function we've cooked up satisfies the two conditions of lemma 2. Right, because lemma 2, well, of course it's differentiable, but the derivative has to be increasing, and the value at the endpoint has to be the same. So now g satisfies that. G prime is also increasing, and the value at the endpoints are the same. So then we can apply the lemma. If those assumptions are true, the conclusion must be true, which is that the function value is always strictly less than its value at the endpoints. So I'm just going to copy that over and apply it to the function g now. G is less than its value at the endpoint, but what's its value at the endpoint? That's simply f of a, as we saw a moment ago. So g of x has to be less than f of a, the value at the endpoint, for any x in the interval. But as we'll see in a moment, that this circled inequality in pink is exactly what we're trying to prove, convexity, after doing some algebra. So why is that? If g of x is less than f of a, I just take this weird big expression for g of x and plug it into that inequality. So I'm just copying that down on the left side. That thing is less than f of a, so I've just copied f of a on the right side. And now you can see pretty easily that you can just do some algebra here. You can add this term, the f of b minus f of a over b minus a times x minus a, add that to both sides. And then you divide by x minus a. So I divide off the x minus a piece. Add this to the right side, subtract f of a over to the left side, then divide by x minus a. And that gives you exactly this definition of convexity. This must be true. Okay, was the algebra too fast? Should I go through those couple steps?
I think I understand the steps.
Okay, good. All right, good. So we proved it. Increasing derivative means you are convex. So just to recap what we just did, f prime increasing is, well, if the second derivative exists and f prime is increasing, then that means f double prime is greater than 0. So I'm going to draw a two-headed arrow because now we've proven that this goes in both directions. If you're convex and you've got a second derivative, that guy has to be positive. And if you've got a second derivative and that guy's positive on an interval, then you've got to be convex. So this is very nice. The reason, again, well, not again, but something which I emphasized last time, the reason we stated this as f prime is increasing rather than f double prime is positive is that this is a weaker assumption. Why is this a weaker assumption? Because if f prime is increasing, I mean, this can be true even if the second derivative doesn't exist. Why is that? Because you could have a function which is increasing but has a kink, right? So if f prime looks like this, it's still true that f prime is increasing, but it's not true that the second derivative is positive everywhere, because the second derivative doesn't exist at the kink. Anyway, that's why we said it that way. But in any case where the second derivative does exist, then this double-headed arrow will be true.
So would that allow us to go back and find whether or not those points are undefined for f prime and see if they were convex?
Oh, you mean in the first example, in the warm-up?
Yeah.
Ah, yes, that's a good point. So go back and look at that. So Um, yeah, so let's see. This guy, even though the first and second derivatives don't exist at this kink, it looks like f is still convex there, right? Because if I draw, uh, is that true? No, it's hard to tell. I would have to zoom in. Maybe it just doesn't exist there. I can't tell by looking at nearby points if I draw a line between 2 points nearby. Is it? No, it won't be convex here because it's constant on the right. So if I pick a point on the right and connect it, that's never going to lie above or below the graph, right? It's always going to touch the graph. So yeah, indeed. Here the second derivative doesn't exist, and it's neither convex or concave. I think that's also true here, just kind of trivially, because it's also constant on the left. Yeah. Good. That's an interesting question. I like that. Okay, other thoughts on the converse now?
I do not have any questions.
Cool. Okay, here's a challenge for you, another one of these rational functions. So we want to find where is this guy convex and concave. So of course we'll need the second derivative. By the way, you can use the quotient rule for this if you like. I prefer when a fraction has numerator 1. I prefer, rather than using the quotient rule, to just think of this as 1 plus x squared raised to the power minus 1. Because then you can use the chain rule instead of the quotient rule, and I like the chain rule better.
That makes perfect sense.
Good. I'm imposing my preferences about derivative rules on you.
I agree. It looks better.
Yeah. Okay, first derivative. What should we do?
So this is going to be negative 1 plus x squared all to the power of negative 2 times 2x.
Good. Times 2x. So, well, I'm not even going to simplify it. There's not really much simplification to do. Well, I guess you could write it like this if you want. Minus 2x over 1 plus x squared squared. You could write it like this if you really want, but alright. Now, using whatever rule you like, either product rule here or quotient rule here, what's the second derivative?
I'm gonna product rule because I think that's quicker.
Cool.
Actually, that's even more chain ruling. I think I'm just gonna use a quotient rule. Wait, no, even more chain ruling. Oh, come on.
You can't win.
Okay, so I'm gonna take the chain rule of the far right and see that we're going to have negative 2 times 1 plus x squared quantity squared minus negative 2x times, let's see, I guess begin left parenthesis. I don't know why I say that, it just helps me organize things. So this is going to be 2 times 1x plus x squared times 2x.
Times 2x. Okay, good. I think that's right. If I didn't make any mistakes transcribing what you just told me. And then, of course, that's all over this thing to the fourth now.
Right.
Okay, so, alright, I guess we have to simplify the top. Because we actually want to know whether this is positive or negative. So, minus minus. Let's see, there's 3 2's, so 2 times 2 times 2 is 8. So there's minus 2 times the 1 plus x squared squared. I'm not touching that. This guy should be, I guess, plus an 8 x squared times 1 plus x squared, is that right? All over 1 plus x squared to the fourth. And now it looks like we can cancel this common factor of 1 plus x squared. So now this is a 3 downstairs, and if that's true, then this guy is minus 2 times 1 plus x squared plus 8x squared. If I do this without making any algebra mistakes, it will be a fucking miracle. X squared.
It's all checking out so far.
Good. Okay, so then last thing, now I've run out of space, so I'm going to start writing equations to the left. This, in the top, minus 2x squared plus 8x squared should be a 6x squared, and then we have a minus 2 left, right? So 6x squared minus 2. I think this is actually right. Over 1 plus x squared cubed. Okay, so now with that done, I will ask you, where is this thing positive and where is it negative? Notice that the bottom's always positive, so we don't have to care about that. Where's the numerator positive and where's the numerator negative?
So the numerator is going to be negative when, let's see. I guess we can. Is there any benefit to factoring out 2?
Sure, you can if you want. So that would be then like a 3x squared minus 1? Good, yeah, so
Yeah.
where is 3x squared minus 1 negative?
I guess it is going to be negative when x is less than 1 over root 3. That is off.
In absolute value though, right? Because it has to be less than 1 over root 3, it has to be bigger than negative 1 over root 3, right? Because if you,
Right.
yeah, so, or, how do I say that compactly? I guess that means negative 1 over root 3 is less than x is less than 1 over root 3, is that right?
Sure.
Okay, so yeah, I agree. If that's true, then this guy is negative, and I think it's positive otherwise, right? Or, like, well, I guess there's a couple points where it's, at those 2 points, it's exactly 0, but uh, if you're outside that interval, if you're outside minus 1 over root 3 to 1 over root 3, then your square is certainly going to be bigger than a third, so 3 times something bigger than a third minus 1 is going to be positive. So I think that means we should be, let's see, I'll say this one. Here it's negative, so negative means you open down, so you're concave. And here you're positive, so you point down, so you're convex. Good, okay. Kind of interesting algebra. I think this is called the Cauchy distribution, or this is either the probability distribution or the cumulative distribution for the Cauchy PDF, this 1 over 1 plus x squared. I forget which one. Either the cumulative or PDF. But, okay. Let me do the answer analysis and then ask if you have questions on this. So, first, remarkably, no algebra mistakes. Indeed, after, quotient ruling this massive thing, you get something with a 3x squared minus 1 upstairs. So it's positive on, minus infinity up to minus 1 over root 3 and 1 over root 3 up to infinity. And it's negative on this interval. It's the only place. Let's see if that makes sense. This is what the graph of the function looks like. It has a maximum at 0, then it dies off and goes to 0 at plus or minus infinity. But you can kind of see, if you just look at this by eye, you can kind of see that in this area it opens down, and far to the right it's kind of opening up. And there's this interesting inflection point right here. So this place where the second derivative is 0 is called an inflection point for what is hopefully obvious reasons, because here it's kind of inflecting or bending, it's changing the direction of whether it opens up or down. Right here it opens down, and then here it inflects, and then it switches to opening up. So there's another inflection point here, of course. So it seems like our answer makes sense. It's concave in here, it's convex out here, and it has 2 inflection points. Good. Okay, thoughts or questions on this challenge?
Not on this challenge specifically, but for whatever reason, I was thinking about what it means when a derivative is a polynomial.
So you're asking what condition guarantees that some derivative, the first or second derivative of a function, is a polynomial?
I'm just thinking about how it looks and why that derivative is not a line yet.
Okay, so yeah, it means, it basically indicates that the function has more curvature, right? So, I mean, as you know, the simplest function, well, besides a constant, if you just have a straight line, this guy isn't curving at all or bending, so his derivative is 0. A parabola is curving a little bit, So this thing you think of as being more curvy than this guy. So now his derivative is going to be aligned. His second derivative is a constant, and I guess, well, it's going to look weird. Maybe it's better for me to state this as, having two derivatives being zero, even though it's trivial in the line case. But anyway, the point is, roughly you need to differentiate 3 times to flatten this, right? Because he's curving, but not that much. A cubic looks like this, so you can kind of see this is in some sense more curvy than this guy, because he's both curving in the far regions, but he has some complicated behavior going on in between where his curvature is changing. So this cubic, as you say, all of his derivatives are polynomials, but they are successively decreasing in order. So you have to differentiate 4 times to flatten him, so to speak. And then you can go on so forth. Clearly, every polynomial has some number that if you take that many derivatives, you're going to flatten it. There's functions that don't have that property. They never get flattened, like the sine function, for instance. So the sine function, this guy is somehow infinitely curvy. He curves forever, farther and farther. I mean, no matter how far you go to the left or right, he's still curving and changing. So you can take as many derivatives as you want, any n derivatives, and you're never going to flatten them. You're never going to get something which is zero everywhere. I mean, it's zero at some points, of course, but it's not going to be. You can never take enough derivatives to make him completely zero. So I don't know. I mean, this isn't really an answer to your question. It's really just a comment because you're thinking about, what does it mean for a derivative to be a polynomial? And I'm trying to argue that it's somehow related by it's related to how often, how many times the function curves before kind of settling on a direction. That's maybe the way to think about it.
I like how sine is a he and is curvy.
Guys can be curvy, come on. Don't be gender discriminatory.
Oh no.
We are equal opportunity here.
Poor math equation.
By the way, it's not just guys that curve forever that never get flattened. Of course, e to the x will never get flattened either, right? Because you can take as many derivatives as you want. dn dx dn of e to the x is still e to the x. So you might ask, why is that? I mean, it looks like this, based on what you've just told me, it seems like this guy should get flattened by enough derivatives because he's not kind of changing his mind infinitely often and curving. And this reason is, I mean, this one's just very special because this guy's not curving, but he's getting faster at such a fast rate. He's both, I mean, the function's increasing, but he's also increasing at a faster rate, so he's kind of accelerating, so to speak, but he's also jerking in a weird sense because his acceleration is getting faster. So this guy kind of bucks the trend that I was just describing, but that's only because he's getting big so fast. He's getting big faster than any polynomial. We will actually prove that later. I mean, those words don't make sense now, but when I say he's getting big faster than any polynomial, what I really mean is that the limit as x goes to infinity of any polynomial you want, it could be x to the power 100, x to the power 1,000,000, whatever, any polynomial over e to the x, if you take x to infinity, e to the x is getting big so fast that the denominator just completely overpowers the polynomial and this thing is zero. That's what I mean by he's getting big faster than any polynomial. Okay, sorry, this is a big tangent, but thoughts on this?
You're recording, right?
Yes, I am.
Good.
That would be a very shitty time for me to realize I was not recording.
Alright.
Cool. Any other stuff?
I have no further thoughts or questions.
Okie dokie. Alright, so that's enough convexity and concavity now. I think we'll come back to review this later just to get more practice sketching graphs, because I think that's kind of useful to get intuition for graphs, but now let's do something else. And to start this off, I would like to tell you one of my favorite stories from Feynman's biography, Surely You're Joking, Mr. Feynman. So it's a story about Feynman who's at a restaurant in Brazil. You may know he went to Brazil, learned to play bongos and stuff like that, and just had a lot of interesting adventures. So here's an excerpt from Surely You're Joking, Mr. Feynman. It's in a chapter, I think, titled Feynman versus the Abacus. Someone else wrote it. He didn't use this, like, describe him by his own name. But anyway, okay. So Feynman's in a restaurant, and they say, A Japanese man came into the restaurant. I had seen him before wandering around. He was trying to sell abacuses. He started to talk to the waiters and challenged them. He said he could add numbers faster than any of them could do. The waiters didn't want to lose face, so they said, yeah, why don't you go challenge that customer over there, pointing to Feynman. Here I do ... so I'm skipping a couple paragraphs. After this happens, they describe first Feynman competes with the abacus guy, adding numbers, then multiplying numbers, and he's kind of holding his own, but not really there's no clear winner. So they keep escalating it and trying to do more and more complicated math to see whether Feynman or the guy with the abacus would be clearly winning. So I skip that part and then pick it up here where they're in Brazil, so he's speaking Portuguese and says raios cúbicos. He says with a vengeance. Cube roots. He wants to do cube roots by arithmetic. It's hard to find a more difficult fundamental problem in arithmetic. It must have been his top-notch exercise in abacus land. So he writes down a number on some paper, any old number, and I still remember it, 1729.03. He starts working on it, mumbling and grumbling. He's working like a demon. He's pouring away, doing this cube root. Meanwhile, I'm just sitting there. One of the raiders says, "What are you doing?" I point to my head. Thinking, I say. I write down 12 on the paper. After a little while, I've got 12.002. The man with the abacus wipes the sweat off his forehead. 12, he says. Oh no, I say, more digits, more digits. I know that in taking a cube root by arithmetic, each new digit is even more work than the one before. It's a hard job. He buries himself again, grunting, while I add on 2 more digits. He finally lifts his head to say 12.01. The waiters are all excited and happy. They tell the man, look, he does it only by thinking and you need an abacus, and he's got more digits. He was completely washed out and left humiliated, and the waiters congratulated each other. So Feynman kicked the abacus guy's ass and, immediately got at least 10 to 3 digits and then down to 2 more to 5 digits, the cube root of that complicated number. So before I tell you the trick, thoughts or reactions to this very amusing story?
I assume brute forcing something like this would take forever.
By brute force, you mean like a bisection search or something?
Sure. Just guessing and seeing what's closer and closer.
Yeah, that's what I mean by a bisection search. So bisection search means you start with one number that you know is smaller than the number you want. So maybe 12 is smaller than the cube root. 13 is bigger. So you say, I don't know, I know this is smaller and this is bigger, so I'm going to try 12.5. And then, okay, it looks like that's too big, so now it has to be somewhere in here. So I'm going to try 12.25, and then you just keep going down, and then if it's too big, you cut the interval in half, and if it's too small, you cut it in half the other way, and then you keep going down until you get more and more accurate. That's bisection search. So if that's what you mean by brute force, then yes, that does not converge very quickly. I mean, it converges pretty. This is actually O of log n. This is a computer science technique for finding roots. It actually okay. I shouldn't have said it doesn't converge very fast. This is order log n, so it actually converges reasonably quickly to the answer, but it's much less efficient than doing something slightly smarter that uses more data about the problem. Okay, so if that's what you meant by brute force, then yes. Other thoughts?
I have no thoughts or questions or ideas.
Okay, well, I will tell you how he did it, which he himself tells in the next paragraph, but instead of putting that paragraph down, I'll just tell you because I want to show a graph. Okay, so in when he explains it, he says, I happen to know that this number, which was very close to the number whose cube root I wanted, 1728, he says, I happen to remember there are 1728 cubic inches in a cubic foot. Or in other words, that 1728 is 12 cubed. So, that doesn't give you the answer. You still have to get the digits, but you have a place to start. You know that it's going to be very close to 12, but a little larger. Okay, so that's fine. But we also know that this cube root thing, that's just some function f of x. So if you have a function f of x equals the cubed root of x, which is x to the power 1/3, we know that you can approximate a function using its tangent line. What do I mean by that? I mean, if here is somewhere in, I don't know, it's probably around here, is that point we're interested in, and the blue curve is the true function f of x equals the cube root of x, you know the derivative gives you the slope of the tangent line, and as you can see, kind of intuitively, if you're really close to the point of tangency, the tangent line is extremely close to the graph itself, right? If you're over here, you might as well not even evaluate the function f of x. You might as well just use the tangent line because they're so close. The error is very small. So what Feynman did is said, well, okay, I don't know how to take cube roots, but I sure know how to evaluate a line. So what I'm going to do is find the tangent line to the cube root function at this point, which is very close by, and do that instead. So, well, this isn't rocket science, this is power rule. So the derivative of the cube root function is simply 1/3 x to the minus 2/3, so I'll just go ahead and put that downstairs. So what's the slope of the tangent line at this point that he happens to know? Well, that's fine. I mean, f prime at 12 cubed is 1/3 times, well, what's 12 cubed to the 2/3, power to a power, 3 times 2/3 is 2. So this is 3 times 12 squared, or 1/3 times 144. So it seems like a lot of work, but this is probably what Feynman was doing when he was pointing to his head and saying thinking, getting this part. So if that's true, this is the slope, and we know this point slope form of a line, I'll just rewrite it. The tangent line is going to be something, if we call the tangent line a different letter, say g of x, I mean that's going to just be g of x is going to be the slope, well, maybe I'll write it in this other way. It's going to be the point that we expanded around, which here is f of 1728 plus the derivative, f prime at 1728 times x minus that point. This is just that trick again of getting a line by, you have the slope times this distance from the point that you have in question. If you prefer, this is like the point slope form of a line. This is the y and this is the x minus, whatever the point you started with. So, I mean fine, we can go through that algebra, but the point is this is the tangent line function. But this is not that bad to evaluate, right? Because this first thing we know is 12. So this is going to be 12 plus what is x minus 1728? Well, x is this thing we care about, the number whose cube root we're trying to take. So that minus 1728, you can see very clearly that's 1.03. So instead of taking this complicated cube root, all you have to do is take 12 and then estimate what is 1.03 over 3 times 144. And this is what Feynman was doing in his head, this sort of division. This division is kind of easier to do. This is basically 1 over, what's 3 times 144? Well, 300 plus 120 plus 12. So what's that? Something like 432 or something. So you can imagine someone who's good at arithmetic trying to, estimate this in their head. Well, they say, okay, I know 1 over 100 is 0.01. So this is going to be about a quarter that, and so it's going to be around 0.0025, and getting more digits by doing that division. It's easy to do division. It's much easier than square roots or cube roots. So anyway, this was very long-winded, but in summary, what Feynman was doing is not evaluating the function itself, because that's hard. He was just evaluating a line, which happens to be very close to the function that he's interested in. Okay, thoughts on this?
I believe that this may be a kind of reference to how you said that scientists approximate things.
Yes, this is the first real example of that we're seeing, I think.
Okay, cool.
Good, okay. I'll show you more examples of that. But first, let me just state the general technique that we use. So So you've now, or you'll shortly finish CD3, so you know how to find tangent lines to graphs. It's pretty simple. You just, in this point slope form, if you like, you get the slope by taking the derivative at whatever point A you're interested in. So then the line is going to be y equals f of a plus f prime of a times x minus a. Why is this the right thing? Because, well, we know if we plug in x equals a, the tangent line agrees with the function there. So this thing is supposed to give you f of a, and indeed if I plug in a minus a is 0, and this term goes away, and it's f of a. So that's the tangent line. So definition, pretty intuitive definition. We're just going to say the tangent line approximation of a function f near a point a is simply the statement that the function f is approximately equal to this thing I've circled in pink above, the tangent line function y, which is, again, just copied, f of a plus f prime of a times x minus a. So I've drawn a picture to try to convince you that this might be a reasonable approximation. If you have some curvy function f of x like this, which is pretty complicated, and as you see, we go to some point a and find the tangent line, f prime of a times x minus a plus f of a. And then if you zoom in to the graph, so this box we're going to blow up, if you zoom in, you can see that this function y, the line, is very close to the graph of the function in question, right? So if you're close to the point of tangency, you can use the line and your error will be very small. This is the same thing we saw a moment ago that Feynman did, except now I'm just giving the general definition for any function f. Okay, thoughts or questions on this guy?
I do not have any thoughts or questions.
Cool. Okay, let's do some approximations then. Okay, so here's a very common example. Funny story about, well, I'll tell you the story afterwards, but anyway, so the example is, suppose we want to get an approximation to the sine of 0.1. So maybe you're doing some problem and you need the sine of 0.1 in radians, but you don't have a calculator. So we'll just do what we just said a moment ago. Make our function f of x equals sine of x. That's the, if you like, the blue curve here that we're going to try to approximate. The tangent line approximation, by definition, says that f at 0.1 is approximately equal to, we have to pick a convenient point a, so I will choose a equals 0. So that's pretty easy. So plugging in a equals 0, the tangent line approximation tells us that f at 0.1 should be roughly f of 0 plus f prime of 0 times, this is x minus a, but 0.1 minus 0 is just 0.1. Okay, so that's our approximation, but we can evaluate all of these things because we know what the derivative of sine is. F prime is cosine. So f prime of 0 is cosine of 0, which is just 1. F of 0 is sine of 0, which is just 0. So I don't know why I'm circling or waving the pen instead of just writing this, but this is 1. So you see this is actually very easy arithmetic to do. It's going to be 0 plus 1 times 0.1, or just about 0.1. So what we found is that if your angle is small, if theta is much less than 1, sine theta is approximately equal to theta if theta is small. And I think I made a reference to this a while back when we were talking about oxygen atoms. I said this approximation we're making is called the small angle approximation, but I can't explain why at the moment, and I will eventually. So now I've actually made good on that promise. This is indeed the small angle approximation, replacing sine theta by theta when your angle is small. So this occurs all the time in physics because sine is a complicated function. It's hard to deal with. But the function f of x equals x or f of theta equals theta, well, that's very easy to deal with. That's just a line through the origin. So this happens. I mean, just to give one more example of where this happens in physics, if you have a pendulum with mass m, and I let go and the pendulum starts moving, so it swings this way, and suppose you want to write down a function that tells you, where's the pendulum going to be at all times, and you want to do that in terms of this angle theta. Well, if you write down Newton's law for this pendulum, you get something which is pretty complicated. It's going to be something like roughly theta double, well, we need the length of this. Theta double dot 2 time derivatives on theta is going to be, I think it's minus root g over L, is this right? The constant's not that important, but minus root g over L sine theta. And this thing, if theta is small, can be approximated. You just replace the sine theta by a theta by minus root g over L theta. And then this function, I mean, now this becomes much easier. Now you're just saying, I'm trying to find a function that when I take two derivatives, I get the function back. But we know a function that you take two derivatives and you get the function back. It's just, well, you need, sorry, the square root shouldn't be there. I got excited and put the square root in preemptively. We want the square root here. Root g over L t, I think. Because you want to take two derivatives, so by the chain rule you get two square roots out, which gives you this thing. Anyway, so theta of t is this, up to some initial conditions or whatever. I mean, but anyway, so that won't, I mean, maybe not all of that makes sense now, but I'm just trying to illustrate for you that, you know, solving this differential equation is hard. Solving this differential equation is easy. So if theta is small, we'd like to approximate the hard problem with the easy problem. Okay, thoughts on this guy?
What is small?
What is small? Like quantitatively? You mean how small is good enough?
Yeah.
Yeah, so you can write precisely how big the error is going to be as a function of theta if you want. So the answer, how small is good enough, depends on the problem in question. Right? You need to know, if you're trying to model something or build something, you have to know how much error can I tolerate, and then you can get a bound and say theta must be this small or else my approximation breaks down. We sometimes call that a regime of validity. It's the regime or the values of theta where the approximation is still good. But for many problems, if you just need, like, you know, 10% accuracy or something like that, then theta can actually be somewhat larger. It can be, you know, 0.1, 0.2, and I think you'd still have reasonable accuracy. Good. The story I was going to tell, but it's a slight diversion, is that the only exam in undergraduate that I ever took that needed a calculator was freshman year chemistry, the first exam. And it's very unusual to need exams for need calculators for college exams. So my TA warned me, warned everyone. He's like, guys, don't forget, you need a calculator. It's the only test where you need a calculator. Bring a scientific calculator, you'll need it. And I was like, okay, sure, I'll remember. And lo and behold, the day of the exam, I forgot to bring a calculator. So I walk into the exam, they hand me things, and I see, okay, you have to do shit like find, you know, for part of some chemistry problem where you're finding, you know, the energy of a photon or something, at some point in the calculation, you had to get sine of 47 degrees. And I thought I was fucked. Then I looked at my wrist and I realized my watch, I wear a calculator watch, but the calculator watch is just a 4-function calculator. It only has plus, minus, times, and divide. It doesn't have sine. So what do you think I did, being, you know, the tricky fucker? I said, well, I don't have sine, but I know this is going to be roughly sine of 45 degrees, which I do know, plus the derivative, which is cosine of 45 degrees. I converted to radians. This isn't actually true because the derivative of sine isn't cosine in degrees. There's some number here, but I happen to know how to fix that. But anyway, I knew it's cosine of 45 degrees times the difference, which is 2 degrees. And I mean, this isn't quite what I did, but the corrected version of this, with, you know, accounting for the fact that this isn't true in degrees, just in radians, this is what I did, and I actually got the problem correct. And I ended up with, I think, a 98% on that exam. So it's good. It's a good trick to have in your belt, as Feynman saw. Okay, so now I will ask you to do something. Suppose you want to take e to the power of 0.02 without a calculator. What would you do?
So according to this approximation style, you're going to have, let's see, and trying to recall things, is going to be about equal to, so I'm going to say that our base value is going to be 0, so we have e to the 0 plus the derivative of e to the x is just e to the x?
Yep.
Well, it needs chain rule, I think. No, wait, why did I say chain rule? Never mind.
Yeah, you're right. The derivative is still e to the x, and you evaluate that at 0, so what's this guy going to be?
It's going to be e to the power of 0.02.
Or no, this one's still 0. Remember
Oh,
it goes like f of x is roughly f of a plus the derivative is evaluated at a, not at x. So the derivative is at a, and then you multiply by x minus a. This is the approximation.
oh boy.
Good. So what do I multiply here?
And it's going to be times 0.02.
Good. I think you know what these numbers are, though. What should this be?
I think so. Overall, it's going to be about equal to 1.02.
Yeah. Good. So, I mean, as you can see, there's nothing special about 0.02. This is just the approximation that you're always going to get 1 in the first slot and 1 in the second slot, so this is roughly 1 plus x for small x, x small. Which is, again, a pretty good approximation. I think I'll show on the next slide what this really is. So, as you say, we should expand about 0, so e to the 0 plus e to the 0 times x, and we get 1.02 as our approximation. If I plug this in Mathematica and ask what is e to the 0.02 actually, it's 1.0202. So, I mean, if you only need, say, 3 sig figs, that's totally fine. It's only going to change way out here in, like, the, what's that, hundredths, thousandths, 10,000ths place. So it's a pretty good approximation. Okay, thoughts on this?
Nothing on this specifically, but I am curious. So, in my lovely chem class, we were talking about significant figures, and we had stuff going out to like the 100 millions. So we only had 2 significant figures.
Yeah, but I mean, the significant figures aren't a function of how big your number is. So, for instance, if you measure something and you measure it in, say, nanometers, and you say something is 12 nanometers, you would look at this and say, oh, of course that has 2 significant figures, right? 1 and 2. But if someone else came along and said, this is, I'm not going to get the right number of zeros, but 0, 0, 0, 0, 0, this is 10 to the minus 9. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. I don't know if this is right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, one too many. Fuck. 1, 2 meters. Anyway, I mean, you see what I'm getting at. You would look at this and say, well, this is just the same number expressed in different units. So why should it have more sig figs now than it did a moment ago? I've just converted units. So somehow all of these zeros, these so-called leading zeros, must not be significant. They're just an artifact of the choice of units I used. So that's why we still say, indeed, even if this is out in like the 100 millionth place or whatever, even though there's all these zeros, you don't consider them significant. It's the same number. They don't matter. Is that the question?
Sure.
It probably wasn't quite what you're asking.
It is the question,
Okay.
but I'm thinking about how they work anyways.
Oh, so you're thinking of why is it useful to track a number of significant figures in a way that obeys these rules, that it's the same in both of these?
What would occur if we had a 0 between this 1 and 2?
A 0 between the 1 and 2. So you say 102 nanometers.
Yeah.
This 0 is significant. This is a so-called trapped 0. A 0 between 2 other significant figures is considered significant. So this would have 3 sig figs. It's a captive 0, if you will.
So now I'm suddenly curious why every single one of them had 2 significant figures, except there's only one correct answer. Asking about I'm just thinking about my chem quiz.
Wait, you're objecting that why is there only one answer for the number of significant figures? I don't understand.
Because all of them had just 2 values.
Oh, all of the things on your quiz had only
In
2
this,
values.
Like in the string of zeros, there's only 2 non-zeros.
Ah,
And
good. Okay.
asking which one had 2 significant figures.
All of them had. Wait, I still don't think I understand the question. You're talking about this thing, the one in meters?
Just the one you made makes for a close approximation, like similar to what this quiz was asking.
Oh, I see. Okay, and I think I understand now. So you're making a comment that this is similar to this
Oh,
example in the quiz.
I think I understand now.
Good. Uh, yeah, I mean, I don't think significant figures are a very good way to do uncertainty. Personally, it's kind of hacky, but um, whatever. Okay.
Anyways,
Other thoughts on sig figs or this exponential approximation?
I do not have any thoughts.
All right, let's bang out the last couple then. Okay, so I'll ask you to kind of speak your thoughts aloud on this because this is a bit kind of a content-rich problem. It's I think very interesting. So suppose I want to paint a sphere. The sphere has a diameter, not radius, of 1 meter. So this is 1 meter. And I want to paint it with a 2 millimeter thick coat of paint. So if you prefer, I mean, I'm drawing this bigger than it would. I'm exaggerating the thickness of the coat of paint just so we can see it in the drawing. But I basically want to add paint. So it's kind of, if you like, I'm, you know, turning this into a slightly larger sphere, which is the old sphere plus an extra shell of paint. And the thickness of this shell of paint on the outside is 2 millimeters. So, I mean, of course, we know what the volume of a sphere is, so we could just compute the volume of the new sphere and the volume of the old sphere and subtract those two volumes. And then that would give me the amount of paint I need. But suppose I mean, that sounds hard. I don't want to take this thing, cubed or something, so I'm lazy. So I claim we can approximate this using a technique very similar to what we did a moment ago. So I'll ask you what I should do. Using an approximation scheme, what volume of paint do I need to get this shell?
So we need the formula for volume here.
Yes, do you know the volume of a sphere of radius r?
I'm gonna make a guess. Is it 4/3 pi radius cubed?
That is correct. Good.
Whoa, that worked.
Nice. I mean, we can derive this later when we do integration, but now that your brain has been trained from doing all those derivatives, you probably look at this and say, oh, it looks like that 3 is almost cooked up for the power rule, and indeed, yeah, we'll see that, but anyway, so that comes later. Now, what should I do to approximate this function?
I guess we can approximate with the known value of a diameter of 1 meter.
Yeah, so what's the radius if the diameter is 1 meter?
It is, well, oh right, it's going to be 0.5. So it's going to be overall 1/8.
Yeah.
Or that line the cubed. Yeah. I skipped steps. Yeah.
So you say this is going to be, So we're trying to approximate the volume at 1 meter plus, damn it, why do I keep doing this? 0.502, right? Because that would be the 2 millimeters. So you're saying we should approximate this as v at a half plus the derivative at a half times the distance between these two, which is 0.002. Is that the claim?
Yes. Good job doing all the work.
Okay, well, I was just making sure I understood what you said. So, okay, good. So, first of all, what's the derivative v prime? Because we're going to need that.
V prime is 4 pi radius squared.
Yeah, do you recognize this formula? What is 4 pi r squared geometrically? Maybe you don't remember. This is the surface area.
Oh, okay. I thought it was something else.
So
What else it could be? Okay, cool. Wait, that is weird. I don't like it.
Yeah, we'll come back and see why that's true in a moment. Right now, that seems very mysterious. Why is differentiating the volume give you the surface area? But whatever. Okay, so let's go back to this problem. So the amount of paint, so it's going to be a sloppy equation, but the amount of paint is supposed to be the difference between the two volumes, right? So it's supposed to be the new volume after the paint minus the old volume before the paint. So this is supposed to be V at 0.502 minus V at 0.5, which is apparently what you just told me. The derivative, which is 4 times pi times 0.5 squared times this thing, which is 0.002. And I think we can kind of just hackily, since we're approximating, let's just, try to get a rough idea of what this number is. Well, pi is about 3, so 4 pi is about 12. A half squared is down to a fourth.
I'd argue that you can solve for the 0.5 squared first and somehow zero out the 4. Well, cancel the 4.
Ah, good. Okay, so you say I want to square this and get a fourth, so I could just write this as pi times 0.002 instead. Yeah, so well now
But that doesn't help us.
no, that's fine. I mean, if you just wanted to get a rough idea of what this was, then you would say, all right, pi is about 3, so that's about 0.006, and I've been dropping units in all of these steps, but of course we know what the units of this should be in cubic meters. So that's about what we need.
All right. Cool.
Good. Okay, so let's see how good. Oh, I didn't actually. Usually when I do an approximation, I like to find the real answer to see how close we were, which I did not actually do here. But anyway, so yeah, as you said, we should approximate the volume around the known value. Use this thing, v prime is 4 pi r squared. The difference is this, so it's about 0.006 cubic meters. Nice. Thoughts on this?
I have no thoughts.
Okay, so let's try to interpret this statement that the derivative with respect to radius of the volume is the surface area. Why is that true? Here's the interpretation. If you increase the radius of a sphere, so this is, I mean, again, this is larger than the 2 millimeter thick coat of paint. I've just blown it up to emphasize the difference. But if this was the old radius, and then you blow it up, or sorry, you add a shell to a larger radius, and you want to find the volume of this small, of the area between these two shells, between the old sphere and the new sphere, which is kind of cut open here, so it's like this shaded volume of, the in-between bits. What would that be? Well, approximately speaking, if you don't care about the fact that this thing is kind of curvy, you could just think of the region between these two shells as a box with a certain thickness and a certain, I guess, the two ends of the sphere would be, if you prefer, the two pieces. I'm not saying this well. We're thinking of this approximately as a box because we're ignoring the curvature of the sphere. What do I mean by a box? I mean, we're thinking of this volume as a box where one of the dimensions of the box is this length, the distance between the two radii. So this is r minus r, is one of these. Then you say, what are the other dimensions of the box? If we're just squishing this into a box, what should the area of one of the faces of the box be? Well, you say, okay, well, if we turn the sphere thing into a box, then this is supposed to be the surface area of the sphere. Because when you unroll this into a box, then this is the surface area, which is 4 pi r squared. So what I'm trying to convince you of is that roughly if you change the radius by a small amount from lowercase r to capital R, you get a volume which is roughly gotten by kind of stretching the surface area of the sphere out through a distance r, capital R minus little r. Right? That's what I'm trying to say by a box, right? You're stretching the surface area of the sphere, which I've drawn as the face, through this direction into the screen, a distance r minus r. That's the interpretation of this. That That's why the derivative of the surface area, derivative of the volume of a sphere is the surface area, because if you change the radius a little bit, that's almost like adding a box whose face area of the box is the surface area of the sphere. I'm not saying this very well, but hopefully this picture is helpful. I mean, just try to find the volume enclosed by these two things, and you can convince yourself it should be basically the surface area of the sphere times this length. You should ask me questions on that, because I kind of butchered that.
I don't believe I actually have any questions. I get the idea.
Okay, so you're happy with this statement?
Yeah.
Okay, I want to make one more comment about this, and well, then we have one more slide. But this is one reason why people like Leibniz notation for derivatives. Why is that? Because in Leibniz notation, you would write dv/dr, as we saw a moment ago, is 4 pi r squared. Now, all right, this is bad math right here. I'm just going to flag I'm about to do something totally wrong, but you probably see where I'm going with this. We're going to pretend that this is not a fraction. We're going to pretend it's a fraction. We're going to pretend this is a small change in volume divided by a small change in radius, and we're going to multiply both sides by dr. This is not a correct equation at all. This symbol has no meaning whatsoever. We have not defined what it means to take dv outside of a derivative. But let's just pretend for a moment. Now we try to interpret this. What should this mean? This should mean that a small change in volume equals 4 pi r squared times, again, the small change in radius. So you can think, if you like, although I really dislike this, if you like, you can think of Leibniz notation as a mnemonic for the tangent line approximation. Because this second line that I've just written with all the words is exactly what we found by the tangent line approximation. That if you want to approximate the small change in the volume, you multiply the derivative by the small change in the argument. This dr, so to speak. So, I mean, again, this doesn't mean anything, but it can help you remember the way that the tangent line approximation works. Okay. Last thing, and then I shall leave you to finish this consolidation document. So, you asked before, how small is small enough? So, if this is an approximation, we'd probably like a proof that the approximation actually gets better as the distance between the point where you find the tangent line and the point where you evaluate the function. As that distance gets smaller, the approximation had better get better, or else it's not a very good approximation. So I wonder, can we rigorously quantify that sort of error and try to prove something about it? So in fact we can. The proof is very short. So here's the theorem. Let f be c1, so it has a continuous derivative, and you define this function called the approximation error, which I'll write with capital E of x. So what is the approximation error? This is just the actual value of the function at a point minus this formula, which is just the formula for the tangent line approximation. So you take the difference, if you like, in this picture, you take the difference between the actual value of the function and the number you would have gotten by using the tangent line, and you call this E of x. Maybe if we want errors to be positive numbers, you should take the absolute value, but we won't do that. The error can be positive or negative for now. Wait, why did I write that f? Damn it. Sorry, there's a typo. Yeah, the left side of this equation should clearly be E of x, not f of x, because I'm defining E of x. That was silly. Okay, so if you define the error this way, then here's the conclusion of the theorem. The limit as x approaches a, so as we get closer and closer to the point of tangency, the limit as x goes to a of the error divided by x minus a equals 0. So notice this is stronger than saying that the limit as x goes to a of E of x equals 0. This implies that. This is saying both the error goes to 0 as you get close to a, but also the error goes to 0 faster than this thing. You know, the denominator is also going to 0. So this is a ratio of two guys that are both going to 0. And if that ratio goes to 0, that means the top is going to 0 faster than the bottom. So this is both telling us that the error gets small, and it gets small comparatively fast, faster than x minus a. Alright, the proof is 2 lines. Literally, it's basically just the definition of the derivative. So here's the proof. We're just going to write down the fraction that we're trying to show goes to 0 and compute it. So the limit as x goes to a of error divided by x minus a. Well, what's that? I plug in the definition of the error. It's f of x minus the tangent line. Okay, that's fine. Now let's look at each of these terms. I'm going to split, since this thing has 2 pieces, I'm going to split this and put the second term, which is when you distribute the minus sign, this is minus f prime of a times x minus a, but the whole thing is divided by x minus a. So when I divide out in this term, those cancel, and I'm just left with a minus f prime. So that's the second piece. What happens to the first piece? Well, the first piece is f of x minus f of a all over x minus a. So that's this piece. That guy still has a limit in front of him. So this is the limit as x goes to 0 of f of x minus f of a over x minus a. That whole thing minus the derivative f prime of a. But clearly the first term is simply the definition of the derivative f prime of a. So this thing is f prime of a minus f prime of a equals 0. Thing minus thing is 0. So that's the proof. I mean, it's almost silly. It's just that, you know, this is the definition of the derivative, so the fact that the error goes to 0 this fast is really just, I mean, almost a tautology. So again, I'm just emphasizing that we're both showing that this approximation gets better as we approach a, and it gets better faster than x minus a goes to 0. So this is kind of a way of quantifying how rapidly the error diminishes. And in fact, later, I think when we do sequences in series, we can prove a bound that will tell you, you know, the error must be smaller than a certain number, and we can prove that. I forget exactly the way that works, but it's you can prove that the error is roughly going to be smaller than some number, I think, times the second derivative at a. So I think that kind of makes sense. I mean, this is just saying that the bigger the second derivative is, the more room for error you have. And that kind of makes sense looking at this picture, because if the second derivative is huge, so this guy is like very sharply concaving, he's opening upwards very fast, then that's just saying that he's going to, you know, bend away from the tangent line faster. So if he bends away from the tangent line faster, there's more room for error. But anyway, we haven't proven this yet. We'll do that later. So that's just a preview. Okay, last slide. So that's everything. Thoughts on this approximation error or any other stuff?
I do not have any thoughts on this specifically. I believe before the meeting, my mother actually mentioned my first piece of lab equipment arrived today, the scale.
Nice. The first piece not counting the pipette, right?
Correct.
Good. Well, it's not enough to do biodiesel, but now you can go weigh things very accurately.
Yeah.
Nice. You can see how many